for partners. Hopefully you found partners. If not, we will try and we'll try and match you up. So you generally have partners unless you've gotten permission for me in a very few special cases to work on projects by yourself. The other thing I had questions about is that, okay, so we turned in something because we had the assignment due, but we have a new idea we like better, or maybe after the lecture today you say, oh, I'd really like to try do that out, or something like that. If you want to change your topic and your project, that's all fine. That's this is normal. I'd say about 10 to 20% of the projects will actually change kind of they won't follow exactly what the proposal is. Probably your proposal is fairly vague still, and this is fine. We'll get feedback to you on whether it's generally feasible or if you need to kind of think about it differently and kind of change some stuff. We'll try and do that over the next week or so. But if you decide you want to do a new project, you want to change it so it's kind of outside the scope of what you said in the proposal, then what you should do is you should submit a new proposal to Canvas. That's fine. You won't lose any points. This is just for our internal kind of record keeping of what you've done. And you should also send email to me and also Maria. So that we can kind of keep track of these things. We know that you've changed it, and that's fine. That's normal. And so the next step will be the data collection report, which is going to be in in 3 weeks. And as that gets a little closer, we'll start talking more about that. But this will be. You should have said something about where you think you'll get your data now. You should probably try and have downloaded it and maybe parsed it and we'll start thinking more about how to represent it so you can do your actual analysis on it. And that'll be the stuff for the data collection report within 3 weeks. But the proposals now is so you really start thinking about your project, right? This is more of a forcing function than you being locked into stone. Yeah.
If we're using GitHub, do you care if we have it private or is it okay to have it public?
So you're working on it through GitHub.
Mm-hmm.
Oh, so that's fine if it's public. Yeah. So this, I guess in some of your other classes, they're concerned about it being public, then the solutions get out. Yeah, so these projects are all, there'll be some things that look similar to previous years, but that's fine. They can be public. Yeah, I hope, in fact, that you can use this project as something you can showcase whenever you're kind of looking for jobs as an example of something cool you've done, right? So it'd be great if it's public and all that. So great. Any other questions about the project? So good. The homework one, I'm hoping they'll be graded by the end of the week. So that I got kind of an initial draft of the grading today, and I haven't looked over everything, but hopefully roughly the end of the week, I think, is when I'm guessing those grades will be out. If you haven't seen, the document hash assignment was posted a week ago, and you'll be kind of taking these idea of k-gramming and then converting it into these vector representations, and you'll be doing that with some small, simple document examples, and that's what that homework is about. Just today, I posted a version for this homework assignment due in 2 weeks. And I haven't updated Canvas yet. I want to just double check, but I wanted to post it today, so you have 2 weeks to go on it. You should basically be able to do probably all of it after the lecture today. There'll be some stuff over the next couple lectures where we'll kind of be discussing some of the related material, but that should also be something you can get started on. Probably the 3 largest homework assignments or the first 4 are probably some of the larger ones. So then it's going to kind of taper off for the amount of the homework assignments you have to do. and the total amount of work. So if it looks like a lot so far, hopefully I'm trying to front load a lot of these assignments, and they're closer when we discuss them, and then you can kind of think more about the project later in the semester. So okay. So any general questions about this? So great. So also we'll try and give feedback on the project proposals, but it'll probably be, for most of you, it'll be pretty light. Like, this seems like a reasonable idea. This is a good idea. It's hard to give detailed feedback formally at this stage. What works really well though is to come talk to me and to tell me and remind me what your project proposal is about, because I can't keep track of them all in my head, and then I can give you feedback that way, either before, a little bit before after class, or for a while after class, or in my office hours. Those are all great times to come ask me about your project. And I'm happy. I've been doing this for a number of years, so I can give a pretty good feedback on interesting directions, what'll work, what probably won't work, and stuff like that. So so great. So okay. So so we'll be talking about this this idea called locality-sensitive hashing today. Okay, and if you remember, we kind of had this pipeline we talked about where we had this kind of raw data, which we kind of mapped. We said, okay, let's just look at this as text somehow, right? And then this text we can convert into this abstract set by like doing these k-grams, and then we did this min hashing, and this gave it into this this vector, and this was kind of this a little bit strange vector where you have some domain and you have this k-dimensional vector in this domain. So you had v1, v2, vk, and each of these vi's was one number between 1 and m. It could have been a k. You could represent this another way, but it might as well just be some number. And we had this property that if you looked at the Jacquard similarity between sets A and B, then this would be the was equal to the expected value that the ith representation of A in this vector was equal to, or I guess this was equal to the probability that VI of A was equal to VI of B. And this is each element of this min hash vector. And this meant that also that the Jacquard similarity was equal to the expected value of this 1 over k sum over I equals 1 to k, of where I got a 1 if VI of A equals VI of B, and it was a 0 otherwise, right? So this was my approximation of the Jacquard similarity based on these vector representation, and that equaled, the expected value was the thing that we wanted. Okay, so there's this similarity function which we thought captured the sets well. We thought the sets represented the text well, and the text was our proxy for this data, which was emails or web pages or something like that. Okay, so we have this framework that we've set up so far, and this is kind of like, this is one example of how you start from some raw data and you get to some nicer representation. And this sort of pipeline we'll see in, maybe less explicitly, but it'll be discussed in, in other parts during the semester. We mentioned some of these already, where there are other ways of representing kind of the meaning of individual words, or just these Euclidean vectors will come up in a bunch of other places as well. But so we somehow get to this representation, and we think this Jacquard similarity is a good thing to try and kind of model. although this was a choice, there were other similarity measures we could have used, but we think this Jacquard similarity is a worthwhile one. And we have this vector representation. Okay, so what locality-sensitive hashing is trying to do is going to be useful now in the setting where, say, I've got n, where n is maybe equal to, say, 1 million, for instance, just as a good number to keep in your mind of these documents, right? So think of it as, say, D1, D2 up to Dn, and maybe I've gone to, I've done k-grams, and I've got these as these sets, right? So as sets A1, A2 up to AN. I've converted them to k-grams, and maybe now I've converted them into these vector representations, and I've done a min hash, and now I have V1, V2 up to Vn, right? Where these vectors were this vector representation. Okay, right? So instead of documents, I now have these nice vectors, and so I would now want to ask two questions. Okay, so the first question one is which pairs of the objects are which pairs of objects are going to be similar, right? And so think of it, I'm going to set some, and by what I mean by this is that the Jacquard similarity of, say, AI and AJ is going to be greater than some threshold tau. Okay, so I'll set some threshold tau. Let's say, I think in your in the homework assignments, it's going to be 0.085, for instance, right? 0.85. Okay, and I would say what pairs of them are closer than this, right? So in database, this would be known as a join to find all these close pairs. And so, I want to do this for, say, which documents are going to be very similar to each other. These are going to be kind of essentially near duplicates of each other. Okay, and this might be that one is a copy of the other one. And then this threshold of 0.85 might be that might be 0.95 as an exact copy or as plagiarism. 0.85 might be something like, okay, they're on the same general topic. They're both documents talking about the University of Utah, like the women's basketball team, right? So if they're both talking about that same, they're both a news article about that same thing, they might have, above 0.85. Or maybe that's 0.6. You'd have to figure out what a good measure is, but you'll set some parameter, and then you want to find all pairs which are roughly on the same topic. Okay, and then this allows you to kind of say, okay, now that I've grouped similar pairs, I don't want to pick in my search engine result, for instance, I don't want to have more than one of any of those things within this threshold in the first 10 results I show, because they're really showing the same thing. I want to give a diverse picture of what's going on. Okay, so that's the first question. The second question is then, so given a query DQ, right, which I can then say convert into AQ into VQ, right, using the same process before if I want to. Then I say, ask which objects are similar, right? So now given a query, just with respect to this one query, I want to find which ones are going to be similar. And again, I'm going to set some threshold tau, and I want to say, return all the ones which are within this threshold tau. I want all the news articles which are close to this. As professors, there are these databases of homework solutions that we might have. You turn in your homework solution, I can look it up into my database and say, return all the ones which are more similar than this threshold. And I can check to see if any look, then go check by hand if there are any of these. All right, so I want to do these operations. Okay, and so now if I naively just compute the distance, this one requires n squared, distance calculations, and this one requires n distance calculations. Okay, so if these data sets are big, n is 1,000,000, this one I want to do super fast. And the first one, 1,000,000 squared is really large. So that one, or it could be 1,000,000,000, and 1,000,000,000 squared is even bigger. These are large numbers, and I don't want to spend this much time. I don't want to check all of them individually. Okay, so I'd like to do something where because presumably I've set the threshold high enough so the actual number of pairs which are close is actually going to be relatively small. It's going to be much smaller than n squared here and much smaller than n here. It could be in most cases the answer might be 0, right? Most of your homework assignments hopefully are beneath the threshold of being similar to another homework assignment, right? So can I somehow get away with avoiding these n different distance calculations? I'd really like to do that. Okay, and so locality-sensitive hashing will be a way that's going to help with these sorts of problems. Okay. All right, so these questions make sense? These are fundamental, important questions that come up all the time. Yeah.
Just a quick question on notation. So with an n hash, like a v1, is that like a vector of like, I don't know, running like 10 hash functions or something like that?
Yeah, right. So with k or t hash functions, I forget which parameter I've used at different points, then probably closer to 200 or 1,000 hash functions to get this to work well. But it could be 10. You can kind of see what's happening at the 10. Yeah, that's right. And so each of those vectors is the result of those 10 elements that each had kind of this property for each individual one. But on average, when you aggregate them together, they work pretty well. You have enough. Okay, so I'm hoping you've seen a version of this question before. I'm hoping you've had a data structures class. Maybe not quite all of you have had data structures class, but probably most of you have. And so you've probably seen something where so you have n, just n, you just have n numbers, right? S1, S2, up to Sn. And this is a subset of just say the real numbers. Okay, and I want to, let's call this set S, and I want to store S in a data structure. So say given a query Q, return the arg min Si in S that is the difference between Q and S. Right, so it's just scalar values. Right, in a data structure class, what's kind of the first thing to use to do this? How would I think of storing these things? So min heap so a heap is the right direction. Think simpler, right?
Sort of list.
Yeah. Okay. So the first thing I want to do is I want to sort in a list. But a list, if something's roughly in the middle of the list, I don't necessarily know how to get to that quickly, right? A list I would think of as being sorted with pointers, and to get to the middle, I have to hop along in the list. So what would you add onto a list? A tree, right? And then build a like a binary tree on top of here, right? So I'm going to have S say, and I'll assume that they're in the sorted order. Right? And so then I'll build a binary tree on top of here, and maybe I store S3. At this location, I'll store S1 and S3, and then and so forth. And then on a query, I can kind of walk down this tree. If it's greater or equal than S3, I go down this way. If it's less than, I go down this way. And I can answer the second question, right? So I can answer Q2 in O of log n time, right? So by I can find the exact location of Q in the sorted order by going down the height of the tree. Right, so hopefully this is familiar from a data structure class. Okay. So this works with scalar values. What if these values are in 2 dimensions instead? Right. All of a sudden, this gets a little trickier. There's some data structures for 2 dimensions, and we'll talk about this next week and higher. Okay, and like in 2 and 3 and in like maybe 12 dimensions, there's some stuff that can work pretty well, maybe even up to 100 dimensions if it's Euclidean and the data is kind of nice. But if instead they're sets, and I want to use the Jacquard distance I don't even have an ordering over them, right? I just can compute the distance. How do I do something like this? I need kind of a fundamentally different idea. Okay. Okay, so I need a fundamentally different idea of how to do this, and this is what locality-sensitive hashing is trying to do. Okay, and so for locality-sensitive hashing, right? So the key ingredient I need is that some family of hash functions where I can draw these hash functions from it, these IID hash functions, with the instance that the probability that H of A is equal to H of B is approximately equal to some similarity between A and B. Okay? So I roughly need some sort of hash like this. And if I have a hash like this, then there'll be machinery that we'll discuss in the lecture today, which will allow us to answer questions 1 and 2 much faster than this kind of brute force approach. And it only needs this sort of hash function property. Okay, so as long as I have a hashing where they happen to try and intersect proportional or exactly with the right probability proportional or with the probability of the similarity, then I'll be able to kind of turn a crank, I'll explain today, and show you how to kind of ask these join and kind of return the near neighbor questions. Okay, and so we've seen with the Jacquard similarity, we have exactly this property that the hash of A, the probability of the hash is exactly equal to the similarity between the Jacquard similarity between A and B. Okay, and so there are a number of other kind of hash properties where this thing also holds. There's, if you look at just one-dimensional data, you can do this. There's kind of a very simple example in the book with what I call the triangle similarity, where this kind of works out in a very kind of intuitive way. But I want to mention another one which will come up in the homework. So that's called the angular similarity. It's also going to have this property that that the probability that there's an intersection is going to be exactly equal to the similarity between the two objects. I'm also going to get this property exactly, and then we'll also at the end, hopefully, I'll discuss the something for the Euclidean distance, and then the similarity happens to be like the dot product. So the dot similarity just between vectors, and this will have something that the probability that they collide is only going to be approximately something like the roughly. I mean, it's going to be somehow proportional to what the dot product is between them. Okay, it's not going to be exactly, and the dot product could be infinite, and so it's a little bit more complicated to deal with the Euclidean case. But it turns out that it's going to use the same idea as the angular similarity. This is going to kind of be the backbone of this approach. So that's why we'll discuss this. This one also comes up a lot in using between if you do a bag of words representation of a document, then the angular similarity, and it's related to what's called the cosine similarity. Those will be used a lot, and we'll talk more about those next week on Monday. Okay, but so the angular similarity, my objects, I'm going to assume that, let's say, A and B are going to be in what's called S d minus 1, which means that these are going to be, so A and B are going to be elements of RD, so they're going to be Euclidean vectors, but such that the norms of them is exactly 1. So that means that these have to be unit vectors. Okay, so it's going to assume that they're unit vectors. If not, the typical thing to do is first normalize them. Just divide them by their norm, and so then they become unit vectors, right? So I can map to, if I have a vector that's in RD, I just take this and divide it by its norm, and this gives me a vector now that's in this SD, right? So this is a blackboard bold on S, and it's actually a d minus 1 dimensional manifold. Think of it as like a circle. So if I have data so this is in R2, so this is 2-dimensional Euclidean space, then this is S1. It's a 1-dimensional circle. Any unit vector in 2 dimensions must lie on this circle, right? So I can think of having a vector, and then this process just normalizes it, so it must lie, so it just points just to that circle, right? So that's what normalization is doing. Okay, and so what the angular similarity between two vectors is, okay, is going to turn out that this is, I can write this down, S angular between A and B is going to be 1 minus 1 over pi of the arc cosine of A dot B. Okay, so this seems a little bit strange. If you use arc cosine of a dot product, there's a pi involved there. Okay, so there's something simpler called I'm going to draw another vector here. So we'll call this one A. We'll call this one B. And so then there's going to be this value here, which I'm going to call the distance, the angular distance, and the d angular between A and B is going to be is equal to arc cosine of A dot B. Okay, so it's just this part here. Okay, so that means the angular similarity is 1 minus the angular distance, but I need to divide by just 1 over pi. So that way that this value, the angular similarity, is going to be in the range 0, 1. So that way I want to have this property here that the probability that the hashes are equal is exactly equal to the angular similarity. So this needs to be between 0 and 1 because the probability is between 0 and 1, okay? So that's why the 1 over pi is coming here. And now this angular distance is just going to be the radial distance. It's the radians of the angle between A and B. So it's the distance I walk on the circle. Or in high dimensions, it's a hypersphere. But I can always kind of slice through the origin and the two vectors, and there's a circle which describes that, and it's always kind of this geodesic on the sphere. Okay, so it's a very natural distance between these unit vectors, this angular distance. And so the angular similarity is basically the right way to think about the similarity between these. And there'll be a hash function, which I'll describe later in the lecture, that has exactly this property. Okay, that the probability hashes applied is going to be equal to the angular similarity. And it's going to be a really simple hash function. Okay, so right now, for locality-sensitive hashing, I need some property like this. And so for the description, we'll describe it's exactly equal, and then I'll mention at the end of the lecture that you can relax this a little bit here. Okay, but I just want to convince you, at least for now, that there are a number of ways that you can come up with some hash function for different similarity or distance functions, right? And we'll mention a bunch of other distances next week on Monday, and I'll mention what's known about if there's a hash function like this for this. Okay. Okay, so this angular similarity is just kind of a formulaic kind of way of kind of flipping the angular distance, and this is a pretty similar thing. Okay, so I'll ask you to work with this in the homework. It's pretty easy to work with. It's you have to call it a dot product and arc cosine. Okay, so let's see. Okay, so what I want to talk about is, okay, so I somehow quickly need to return all the things which are close by, right? I quickly need to return all of the objects, from this large set. And let's say a query, I want to return all the things that have the same value as the query. And so I'm going to put them into a data structure, right? And it's going to use like this, kind of like this vector representation. I'm just going to store this a little bit more carefully with some more hashing, right? We've already layered 2 hashes. We're going to layer a 3rd type of hash on top of here. Okay. So what can I do quickly with the hash? I know that, so I'm going to have this property, the property that hash of A equals hash of B is going to equal to the similarity between A and B. Okay, and I want to say if the similarity is above a threshold, I want to almost always return it. And if it's below the threshold, I want to not very often return it. Okay, so I can think of drawing a picture where this is the similarity between A and B, and this is the probability that H of A equals H of B. Okay, so they both go from 0 to 1. Okay, and what I'm starting off with, I start off with the property this, right? So as the similarity gets more similar, the probability that they collide is high. But what I would like to do is I'd like something that picks some threshold where I have some threshold tau. And if the similarity is above the threshold, I want to say, okay, these are similar. And if it's below, I say they're not. Okay, this pink curve is a little bit idealistic. I won't be able to exactly achieve this, but I'm going to do something close. Okay? And I want to do a data structure so I can return this quickly. So I want to somehow amplify this one hash function. I've got T of these hash functions. How do I amplify this effect? Okay, so I want to somehow combine together the hash functions so that the probability it's above, that I want to only return things if if say on, let's say if 2/3 of them have collisions. How would I put this in some sort of, put them together in like a data structure? Any thoughts on this? Okay, so one way of thinking about this is that I'm going to have one hash function. So let's say I have two hash functions, and I'm going to have this this domain. And I'm going to say if things are similar, that means they should be nearby in this domain. I'm going to put them into these sort of these buckets. Okay, so if things are close, they're going to tend to fall in the same bucket. And if things are far apart, they're going to be in these different sort of buckets. Right? A hash function is generally, this is generally the property. If they're more similar, they're more likely to fall into buckets. And I can store this in a hash table, and then if I have a query, right, I put the query in there, and everything in the same bucket I can return. Basically, in as much time as I can just enumerate the things in the bucket. I store them in a list or something, and I just enumerate them. Okay, but now I can think of having two hash functions. Right, so actually, this hash function is actually dividing it like. So something like this. So now each of these points actually gets mapped. It's got a hash 1 value and a hash 2 value. Right, so now these points now have 2 coordinates, and the query will have 2 coordinates as well, and maybe there's some other data points in here also. Okay, so now instead of having two hash tables for each one and a different hash table for each two, I can create one big hash table. It's now two-dimensional, but I just unroll this into a single array essentially, and I have one big hash table. So one big hash table. Okay, so then I have, instead of m, instead of a domain of m, I have an m by m domain, or just an m squared dimensional vector. Right? And excuse me. So on my query, if it falls in the same cell, which means on both hash functions it collides, then I can return this object. Right? So then I can say anything that falls into here is going to be much more likely to have a collision. Okay? So I can build a data structure like this, and this is somehow going to amplify this probability. What do you think it's going to do to this red curve? So if I use this structure, I use two hash functions instead of one to create one meta hash table, and this is called a band of hash tables. Right, so this is called a band. Okay, what is it going to do to this red curve? What is it going to look like? Just high level. S-curve, yeah. So someone mentioned S-curve. It's not going to quite start looking like an S-curve so much yet. Something simpler is going to happen. Why? Just do this.
The slope increases.
Well, in some parts it will increase, but just like it's going to move. So the probability of a collision for any values is going to go down. So somehow it's going to look like this, right? It's going to be below here, right? So if I do so as I do banding, I'm going to be pushing this function down and also over to the right. Okay. Okay, and so, well, maybe this is helping me achieve this pink curve, But all I've done is I've reduced the number of the false positives, right? A false positive would be something I returned that wasn't actually close. I've kind of tamped those down. But I have a whole bunch of more false negatives now. Something that has dissimilarity, now the probability of it colliding has also gone down, so that's not good. Okay, so this is one data structure trick I can use. What's another? So I think this is kind of overly harsh. So I like to think of this as so it's like the Papa Bear approach, where I'm being too harsh with these hash functions here. I'm making it too hard to find a similarity. I always want to find that perfect match, and it's tough to do. So how would I go the opposite direction? How would I increase the probability that I find a collision? Yep.
Look if they're similar to either hash function.
Yeah, right. So this is kind of like an and. It has to be in both. I can also do an or. I can store two different hash functions, right? So I can do hash 1 and a hash 2. Right, and now I can think of having these points, which gets to put into both here. This would be the data, and then I have a query, which is put here. Okay, and so the query only succeeds. I return the set here. I also return the set here, and I find the intersection of these two things. Okay, and so I can have either of these work, and the effect of this is going to be increasing the probability, right? So this is kind of the or, and this is like the and, right? So if I do an or here, and I call this this is extra forgiving, so like, you know, so it's like the mama bear approach. I'll keep giving them extra chances. Likes the porridge. Okay, it's a little soft. You know, and so it doesn't mean to stereotype the actual the gender connotation here, but I'm creating too many false positives now, right? I'm going to say something right here, which is below my threshold. I'm going to have a higher probability of returning it. I somehow need to put these together, and so kind of doing putting these together is going to be kind of the addition of these two is going to be the like the baby bear approach, and it's going to be a good mix of these two things, right? And so effectively, what's going to happen is that, what's a good color you can see here? Okay, I'm going to get something that's going to look like this. I'm going to get a curve by somehow putting these two together that is going to do some ands and some ors, and it's going to look like an S-curve here. And so it's going to try and approximate this pink curve better. Turn out the more hash functions I can use, the better I can approximate the pink curve. Yeah?
I still don't follow how ordering them increase the probability. Can you explain that?
Sure, yeah. So, okay, so each object gets hashed twice, right? And so I'm gonna, yeah, so what should happen is I should return this one even though it only matches in one cell, right? And if for instance the other query had been here, then I would have returned this guy and this guy. But even though they don't align in both cells, so if I would have done an and, it wouldn't have counted. And if I would have just used one hash function, it wouldn't have happened. But now I have two chances. So effective, it's not exactly twice the probability. It's kind of, there's some dependent structure going on here. But I'm increasing the probability. I give multiple chances, right? Okay, and so it's going to only increase the probability. If I get it the first time, that's the red curve, I will return it. But then I could also hit the second time, so that'll only increase my probability of returning it. And it's going to look something like this green curve. Okay, so how do we put these together? So the basic idea of banding is I'm going to think of having hash 1, hash 2, hash 3, hash 4, up to hash t, right? And so I'm going to think of these hash functions as right. So I'm going to store all my data in these hash tables, okay? And so all of each data point, and so then I'll have these implicit, let's say these columns in here, which you don't so much need to see, which is maybe good because I chose that color. But then I'll put A is going to get hashed into each of these, right? And then the same with B will get hashed into each of these. And then I'll have some C. And each of these is, so inside each of these. Okay, and then I'll think about doing a band. So this will be a band. And so I'm going to have of B hashes. And this is going to be, and I'm going to require an and over all of these. And I'm going to have a bunch of these bands. Okay, so I'm going to have, this is band 1, band 2, up to band R. Let me just make sure I have the notation consistent with my notes. Yeah, great. Okay, so I'm going to have R different bands, and each band is going to have B hash functions. Okay, and I'm going to have over all of these, I'm going to have a band 1 or band 2 or band R, right? So each band will be like a super hash function, right? So I'm going to create these super hash functions. I'm going to create R of these super hash functions. And in any super hash function, it has to satisfy B different hashes. But then I can take an OR over all of these. So that I can hit any of these super hash functions. Right? So now each one of these things, this whole set here, this is one hash table H1, right? And then this will be H2 and HR, right? So I'm going to have R of these hash tables, and I'll query into each of them, and if any of them returns, then I say I have a collision. Okay, and in order to return in any one of them, I need to satisfy B different hash functions, right? So each HI is a meta hash function that requires an AND hashing over B different hashes, right? So I'm layering another kind of family of these hash tables on top of here. Okay, and so this is the underlying structure of how you can kind of amplify. You can turn this kind of straight line curve into this S curve, where the ANDing pushes it down and the OR pushes it up, and you combine these together, and they look like these look like these functions here, right? So it's going to look kind of like this function here. This is with B equals 3 and R equals 5. And I'll work through, let me just work through the probability. It's not too hard here. All right, so I'm going to do banding with B hashes in band and R bands, which are the meta hash functions. right, where I've combined these together. Okay, so let's do the analysis of this is pretty simple. It's illustrative, but it's good to just see how it works. So I'm going to start with, I'm going to assume that I have some S is going to be the similarity of two objects A and B. So that means that the probability that any hash function collides, this is the probability that HA equals HB for any hash function in my original family. Okay, and so now I can say that S to the power B is going to be the probability that all hash functions in one band collide. Right, so if I raise it to the power B, it's a number between 0 and 1. I raise it to the power B, that's the probability that all the hash functions collide inside of one band of size with B hash functions. Right, but I want to look at 1 minus S to the B is going to be the probability that this is not all hash functions collide. So as long as any one misses, then this is the probability. Okay, so if anyone misses, it's 1 minus the probability that they all hit, right? Okay, and then 1 minus S to the B to the power R is going to be the probability that that in no band do all hash collide. Okay, so this is the probability for any one band that I don't have a collision. And then if I have R different bands, they're all independent of each other, then the probability that none of them collide, none of the bands collide, is that raised to the power R. And so then I'm going to have some function f of s, which is going to be 1 minus s to the 1 minus s to the b, all raised to the r. So this is the probability of at least one band, finds a collision, right? Okay, so this probability of a collision, once I do this banding with each hash function, each meta hash function in a band has B hashes, and I have R bands, is 1 minus quantity 1 minus S to the B raised to the R. Okay, so not too complicated, right? But this is what we want to analyze, and when I plotted it, this is the function I'm plotting. This is what gets me the S curve. And this is with B equals 3 and R equals 5. Okay? Okay, so I can change these parameters. So let's see. I plotted B equals 3 and R equals 15. How is that going to change it? So I've increased the number of bands. So it's going to move to up and to the left, right? And this, the other one was over here before, right? So I moved it over to the left, right? And now if I increase B to 6, so this was B equals 3, now B equals 6, it's going to move it back to the right, right? And as the larger B and R are, they're also getting kind of sharper. Okay, let's see, what else do I have? B equals 10 and R equals 15, right? So it was this, so I've increased B from 6 to 10, and else even further to the right. Okay, and the B equals 8 and R equals 100, and it's starting to look pretty reasonable. I'm starting to get you can think of there being some threshold tau here. Right, so about tau 0.055 or something seems, I'm doing pretty good. These are the false positives, and those are the false negatives. And they're only, like, I get some false positives and false negatives, but they're generally pretty close to the threshold, right? And if you go back, we chose the Jacquard similarity because, well, there's min hashing works really well for Jacquard. And we modeled our k-grams in one way or the other so that we made some modeling there. So, don't trust the Jacquard similarity as being kind of as being the gospel. There's this pure, that's really what the right threshold is. Allowing some factor near the threshold, you probably shouldn't care too much about. If I have false positives and false negatives, but they're really close to the boundary, probably not so big a deal. Right? So at this point, I needed 800, right? So this needed T is equal to R times B, which is 100 times 8. I needed 800 hash functions to get this S-curve. This is not a perfect threshold function, but you know what? This works pretty well, right? The ones that I miss are going to be close to the boundary. Okay. Oh, here I put a bunch of them together. Right, so this was the last 8. 8 and 100 was the sharpest one, and this is 3 and 5. Right, you get a lot more spread out. It doesn't look that big a difference, but it's really you can really tune much more here. So I do pretty well already with only 15 hash functions, reasonably well. But as I crank it up, I can kind of I can do much better. Okay, so there's one more. In order to actually use this, I've kind of showed you you can move it left and right a little bit, and I get steeper the more hash functions I use. But typically, you're maybe going to be given, remember, you're going to be given some threshold tau, let's say equals 0.6. Okay, how do I, and let's say, and then the homework you're going to be asked, say given t equals 1,000, how do I choose R and B? Okay, so if you had to do this, what would you do, right?
Start small.
So start small. Yeah, you can start small and then do what? But yeah, and plot. Okay, so I plotted these. I took out a plotting program and I wrote this function. I put in different values for R and B, and I saw what happened. And that's a pretty good way to do it. Okay. You can also there's kind of a shorthand formula where you can you can do some calculus and find out where the steepest slope is, and then solve for R and B. And there's kind of this. You can say the slope, you can make the steep slopest, the slope steepest at tau if you set, if it satisfies roughly this. And then you can more or less, as kind of a shorthand, solve for B approximately negative log base R of t, and then R equals t divided by b. Okay, so this is not not precise, but this is a good starting point usually. Okay, so this is a good starting point, but don't trust this completely. This will kind of get you in the right ballpark, and then you can kind of adjust it there by plotting. I recommend plotting. It's very fast to plot. You can use that. You can do that a couple times, and as you adjust your threshold. Okay, so this is how banding works. And I'll ask you to kind of analyze this and work through this a bit in the homework. I think the bonus question is to actually implement it. So to see it working, you really need to you really need data at a pretty large scale before this really kicks in as being useful, as that much better than doing brute force. But I think in the days that we have, it might start kicking in. Although I'm not sure we've designed it just right for that.
Which type of banding did you use to plot those curves? It's like n or?
So I plotted this function, 1 minus quantity, 1 minus s to the b to the value r, right? So I just plotted this as a function of s, right? So I said this is f of s equals this function, and that evaluates to something, the y value is between 0 and 1. So this is the x-axis, this is f of s. I guess that didn't come through here. But.
So s means here, there's a collide, right? Collision.
Means I found at least one collision among the meta hash functions.
Okay, for instance, if b equals to 3, how do you define there's a collision?
So if b equals 3 and then r equals, say, 5, right? That means I have I have 15 hash functions. I have split them into 5 groups. In each group, I say there's a collision in that group if all 3 of the hash functions have a collision. And I say and that's called a band has a collision. Overall, I say there's a collision if any band has a collision. If at least one has a collision, then I say overall there's a collision. Okay, and how the data structure works is I have these 5 meta hash tables, and I query into each of them, and I return a set, and I take the union of these sets. Right, and that's my final returned answer. Right, each one of the banding kind of forces it to have fewer false positives, but then I kind of amplify this by repeating this so I don't miss too many things. So that's why I have multiple bands.
So when we're trying to find the parameters b and r that satisfy some like tau, are we trying to make tau line up with the curve at like a probability of 0.5 or at the greatest slope, or are those the same?
Yeah, it's not exactly the same thing. There's not a perfect answer for that. You can trade off the false positives and the false negatives depending on what you think is more of an issue. There's no perfect right answer, but you can think of you just try and put it somewhere in the middle. I'll ask you to do this, and if you get kind of about right, then you should be good. Yeah. Kind of up to you a little bit. You see it. You could see in a research paper or in like a demo you turn into your boss, and you could use either. These are all valid things to do. Yeah. So okay. All right. So I have about 20 minutes left, and I want to show you that angular similarity hash function. Okay, and it's going to show some cool stuff about high dimensions as well. Okay, so I'm going to have S angular, which is going to be from S d minus 1, S d minus 1 to 0, 1. And so in particular, for these two vectors, it's going to be 1 minus 1 over pi arc cosine of dot product AB. All right, so that's the angular similarity, and it's going to have to do with this picture. I think is very useful. There's some domain here, and turns out I can always sufficient to think in 2D, because there's always some two-dimensional subspace that goes through the origin and A and B. And I can always think about this subspace. Okay, we'll talk more about high dimensions when we get to kind of the PCA section, but I can think about this two-dimensional picture that's valid. Okay, and so I want a simple hash function that's going to, and so this is described better in the textbook than in the actual notes. So if you're looking for it. So my family of hash functions will be defined by, so I'm going to have this family of hash functions h angular, and an hash function u will be defined by u where u is going to be is going to be chosen uniformly again over this domain s d minus 1. So I'm going to pick a random unit vector, a random d minus 1 dimensional unit vector. Okay, and so that will be, let's say, u here. This is my random unit vector u. Okay, and then the hash function is just going to be defined as it's going to go from, it's going to be super simple from this domain of these vectors, and it's going to map to a -1 or a +1. So now the domain is not some big m-dimensional space, it's just binary essentially. Okay, and it's in fact hu on a vector A is going to be defined as the sign of the dot product of u and A. So that's all the hash function is. So I take this u, and basically I take the dot product, and what this says is that I take a perpendicular to it, and if they're on one side of this half space, right, so this is now a d minus 1 dimensional hyperplane essentially, and if it's on the u side, they get a +1. Their dot product is +1. So A and B both get a +1 for this dot product. So if I picked another hash function here, if I picked another u, so if I pick u prime, I'm going to get a different, so this is a different half space. Now A is going to get a -1 and B is going to get a +1, right? So I'm going to get here h of u of A is going to be +1, h of u of B is going to be +1, h of u prime of A is going to be a -1, h of u prime of B is going to be equal to +1. Okay? And the proof isn't so hard. I've got some version written up in the book. It's kind of technical a little bit because you have to make it self-contained. You have to prove you only have to worry about this setting in 2 dimensions. But once you have it in 2 dimensions, you're basically like the probability that I have A and B have different signs is basically going to be proportional to, if I look at this just in 2D, I look at the orthogonal direction, and that has to hit in this kind of this angular distance here. Right? If I look at the orthogonal direction and it hits in that window, they're going to have different signs. If it doesn't, then they're going to have the same sign. And if you remember the definition of the angular distance, it was basically proportional to that length. And so so the probability of the collision is that it doesn't fall in there, which is basically 1 minus the angular distance once it's been normalized properly. Okay, so that's basically the whole proof. To do it formally, it's a little bit more technical, but so that's basically how it works. Okay, so this is a kind of another hash function. Yeah.
So how did you choose u prime?
Good. Right. So what I was going to say is what's missing is I basically have this step, which I have not told you how to do, and it may not be entirely obvious. Right. So this is probably what you're asking about. How do I choose u or u prime, this random unit vector? It's a d-dimensional vector that has to be restricted to a unit vector. So I want a uniform probability over this hypersphere is sufficient to do it. Right? So how would I generate a random unit vector? Does anyone know how to do this?
Generate a random vector and divide it by the magnitude.
Okay, yes. So turns out not right, but that's a very good and very common guess. So, so I want a uniform over SD minus 1, and the guess, which most people have, what works is I can do a, let's call this something else. I can do a P where I do a uniform, say, let's do -1 by 1, right? So just a unit scalar, any scalar, and scale it so it's in -1 to 1. And I do this, times d, and then I set u equals p over the magnitude of p. Okay? So it turns out this does not work, and the reason for that is if I think about what's happening here, is I'm generating points inside of this box. Okay, and then for each of these points, given the origin, I'm forcing them onto the, like I'm making them kind of a unit vector by forcing them onto the circle inside of here. And so if I just sample points inside of the circle, then this would actually work. But the problem is that there's more probability in the corners than there is along the boundary here. And I didn't draw it perfectly, right? So I've got some extra stuff going on the bottom. But there's more probability in the corners. And so those parts of the sphere closer to the corners are going to get kind of overpopulated with these random samples, right? And then if I don't have the right probability of a unit vector, my probability here isn't going to work out. And so this actually doesn't work. Okay, so doing it like this, which is the really intuitive thing to do, doesn't work. Okay, so if I'm in 2D, one thing I can do for R, D, right, where D equals 2, I can use something called rejection sampling. So I can say do P uniform, say -1 to 1 to the power 2, and say if the norm of P is greater than 1, it's outside of the ball, then I start over. So then if I don't start over, I have to reject. Otherwise, then I can set U equals to this. Okay, so this works, and this works in high dimensions as well. The problem is in high dimensions, something kind of really wacky goes on, and that these probability of falling in the corners gets proportionally larger and larger. Okay, and I think next week, Wednesday, we'll actually go through this probability. And it's kind of it's deceiving, but with probability 1, close approaching 1 as D gets larger, you're going to have to reject it. And so this will be a really slow process. Okay, so this doesn't work that well. Okay, so that's the common first and second approaches to doing this. And neither of them will work because we're going to be in 100, 1,000 dimensions. And at that point, the rejection sampling is not going to work, and this will have way too much error. All right, okay. So it turns, oh, yep.
Is it using inverse trig functions, uniform distributions, 0 to 5?
Yeah, so you can do this. You can do this with inverse. It's going to involve some trig, and there's a way to generate, like if you're on a circle, you can basically generate a number between 0 and 2 pi, and then you can map it to the circle. And there's a way to actually do this recursively in higher and higher dimensions. This becomes numerically really unstable in high dimensions. And mathematically it works, but there's some like numerical issues that come up in this approach. Turns out there's going to be a simpler way how to do it. Instead, what I'm going to do is to generate this So uniform on SD minus 1. I'm going to first step, I'm going to generate a G from a G-dimensional Gaussian distribution. Okay, so if you don't know what a Gaussian is, it's 1 over 2 pi to the d over 2 e to the negative x squared divided by 2. Okay, so this is a probability distribution. High-dimensional Gaussian is kind of in 2D, you know, for 0 here, it kind of looks like this. It's kind of this bump thing. The property of the Gaussian distribution, and so then basically U is going to be, then I can just do this. I can just normalize this. It turns out you actually don't need to normalize it. All the math before worked without normalizing it, but to make it uniform, this works. Okay, the Gaussian distribution has the property that if it's no covariance structure here, then in any direction it looks like a Gaussian. So in order to generate G, so if I look here, G is actually going to be G1, G2, GD, where each GI is going to be from just a univariate Gaussian distribution, which is even simpler. This is just going to be 1 over square root 2 pi e to the minus. Okay, so I can generate these independently, and I can just put them together in a vector. And it turns out that this is going to be symmetric in all directions. The Gaussian is a very special distribution that has this property. There are things that work similarly for and so I need this for Euclidean distance, and if I wanted, this is involved in the hash for Euclidean distance, the LSH, and there's a way for doing it like an L1 distance instead, and there's a family of functions that have some property like this. Maybe we'll talk about that on Monday. But okay, so I can generate these independently, each IID, and put them together, and this works. This is a very special property of the Gaussian. Okay, but I have to generate them from a Gaussian distribution, and to do that, I need another trick called the box Similarity transform. Okay, and this is also pretty cool. I'm going to generate U1 and U2 both from a uniform 0, 1 distribution. So I start with 2 uniform scalars between 0, 1. Okay, and then I'm going to generate 2 Gaussian random variables, G1 and G2. This one is going to be -2 natural log of U1, this is a square root, times cosine 2 pi U2. And this one is going to be -2 natural log of U1 sine 2 pi U2. Okay, so I get 2 uniform random variables between 0, 1. These I can generate easily using any built-in function. And then I do this transformation, and I get 2 Gaussian random variables. Right, and I do this d over 2 times, and I can fill out this vector. And then this vector I can normalize in order to get a unit vector. Okay, so this is a really useful trick. Okay, so that, this is very powerful, and this will come up. This trick we'll need to use this once or twice later throughout the semester as well. That I can generate these random uniform distributions using this Box-Mueller transform, and then this gives me a Gaussian, and the Gaussian is symmetric in all directions. So that means I can then normalize those vectors, the multidimensional Gaussian. Right, and I can generate them coordinate-wise as well. So so that's pretty cool, I think. And you will do this in your homework. So it shouldn't be too hard to do this, right? This is a pretty simple thing once you do the algebra. Okay, and then on Monday next week, we'll talk about a bunch of different distances as well and how they relate to LSH. And we'll continue more on this topic in general next week.